Assalamualaikum and hi everyone. My name is Ni Aisyah Nelly binti Nih Ahmad Khan. My metric number is 1232766. Today, I'll be presenting a topic on the application of differential equation and its solution using Mathematica. The topic I'll be focusing is modeling the spread of an infectious disease using what's called the SIR model. This presentation is based on the same topic as the poster I have submitted, but now I will walk you through each part in more detail. In mathematics, differential equations play a crucial role in modeling dynamic systems in real-world scenarios. One significant application is in epidemiology, where the spread of infectious diseases can be modeled using differential equation. When COVID-19 hit, models like the one I will show today became critical for governments and the health organization to make decisions. The susceptible, infected, recovered SIR model is a classical example that uses a system of first-order differential equation to simulate the transmission of a contagious disease within a population. It used a system of differential equations to describe how people move from being healthy to infected to recovered over time. The problem we are looking at is to model and predict the behavior of an epidemic using the SIR model and solve it computationally with Mathematica. This type of model is not new. The SIR model was first introduced in 1927 by Kermit and McKendrick, and since then it has been used and adapted in many studies. During the COVID-19 pandemic, researchers and government applied this model to understand how fast the virus could spread and what interventions like lockdowns or vaccination could help flatten the curve. Mathematica, like Differential Cloud, the software I use in this project, is very powerful for solving and visualizing such differential equations. The SIR model divides the total population into three categories. ST for susceptible, people who can catch the disease. IT for infected, people who have the disease and can spread it. RT for recovered, people who have recovered or died and cannot spread it anymore. The changes in each group over time are modeled using this system of differential equation, like this formula above, where beta is the infection rate and gamma is the recovery rate. This means that susceptible people became infected at a rate proportional to both how many people are susceptible and how many are infected. Infected people recover at a rate determined by gamma. Now, let's look at how this model is solved and visualized using Mathematica with Differential. First, we define the parameters. We assume beta equals to 0.3 and gamma equals to 0.1, meaning the disease is quite contagious and the recovery rate is moderate. We also define our initial values. 99% of the population is susceptible, 1% is infected, and 0% recovered. Using Mathematica's Differential and the solve function, we solve this system of differential equations over 100 days. Then we use the plot function to visualize the SIR curves. The output graph clearly shows how the disease spread. Okay, now let's look at this graph. The first one, the infected group spikes early on and then drops. Next, the susceptible group decreases steadily. Lastly, the recovered group increases over time. This shape, especially the peak of the infected curve, helps us understand when the outbreak is at its worst. Now, let's discuss the result. The graph shows that as more people get infected and then recover, the number of susceptible people drops. Eventually, the infected group also goes down as fewer people are left to infect. Meanwhile, the recovered population increases. This is the basis of what we call herd immunity, Once enough people have recovered, the disease can spread as easily. The peak of the infected curve indicates the most critical point of the epidemic. Adjusting beta and gamma allows simulation under different conditions like mass use and vaccination. If we increase the recovery rate, gamma, for example, by improving healthcare, the infected peak becomes lower. Next, if we reduce the infection rate, beta, like wearing mask or reducing contact, the spread slows down. This makes the SIR model useful not just for prediction but also for testing different strategies in public health. In conclusion, differential equations are essential tools for understanding the dynamic of disease spread. Using Mathematica Wolfram Cloud, we can solve this equation numerically and visualize important trends that assist in public health decision making. The SIR model provides foundational insight for more complex epidemiological models. Last but not least, these are 3 references that I use. Thank you for listening to my presentation. Bye!